infinity, and I put in x is -1. Okay, so I'm going to get -1 to the n over n from 1 to infinity. Does that converge? Does it converge?
No, because so it's
That's right, it's 1 over n. Remember, you need to have a power greater than 1 for this to converge. This is the harmonic series, so it diverges. Actually diverges. Right. We saw this, right? 1 plus 1/2 plus 1/3 plus 1/4, blah, blah, blah. That actually diverges. Right? You can see that by using the integral test. Right? You look at the integral of 1 over x from 1 to infinity. Right? That diverges. Okay. Okay. So in fact, we know it diverges here. Okay. Okay, now I'm going to ask you a question. Could we converge at -2? Could we converge at -2? What would happen if we converged at -2? Jump on to bring in the symmetry. What would happen if we had convergence at -2? Then we would end up with by the lemma here, what's going to happen? Bigger than 1? What is bigger than 1? Speak. Go ahead and speak. You can speak, right? No, speak in English, please.
The absolute value for -2 is bigger than 1.
Yeah. So what would happen is that we should have convergence at -1, right? If we have convergence at -2, then that would mean that we have convergence at -1, right? In fact, it would mean that we have convergence on this whole thing here, right? But we know that we don't have convergence at -1, so we can't. So this is impossible, right? There's no convergence here, and we can't. What about over here? Suppose I have like at 1.1. Could I have convergence there? No, the same reason, right? Because if I had convergence there, then I'd have convergence at -1, right? So what I know is that outside here, it's all divergent. It's all divergent out here, right? So this is my domain of convergence. This is my domain of convergence. This is all of the domain of convergence. Right? This is all of the domain of convergence. Right? Okay, let's do another example. The game that we're gonna play right now is called finding the domain of convergence. So finding the domain. Okay, actually, so I forgot to say one thing down here. So when if this is A, and this is A plus delta, A minus delta, and you have convergence on, if your domain is something like this, then in that case, delta is called the radius of convergence. Radius of convergence. The radius of convergence. And the reason for this, why is it called a radius? You know, it doesn't look like this. It doesn't look like a disk. The reason it's called the radius is because once you get into complex numbers, then it will actually turn into disks. So once you leave the real numbers and start talking about power series with complex numbers, then you have a disk. You actually have a disk, and then with a radius. So radius of convergence, right? So the radius of convergence here is 1, right? As a radius. The distance to the center is 1. Maximum distance to the center is 1. Okay, so let's do some examples. First example is okay, so the first example is the same as what we were just talking about. So in fact, we already worked this out. Okay? We already worked this out. We know that the radius of convergence is 1. Okay. But I'm going to do it in a different way just to show you a different method. Okay. Okay. So the idea is use the ratio test, see, on the absolute value use the ratio test on the absolute value. Because why? If it converges on negative RR, it does so absolutely. So here's the idea. Here's the idea. If this thing converges on some interval, it does so absolutely, right? So let's just check for absolute convergence. So let's just check for absolute convergence. Okay, so we take our thing and we take the absolute values of it and we do the ratio test on it. Okay. So maybe I'll let you do it as practice. Take 1 minute and try the ratio test on this and tell me what you get. Yeah.
There is a factorial on the example.
Oh yeah, I'm sorry. What am I doing? Sorry. No factorial. And this should be from 1. Sorry. This should be from 1 because there's no factorial. This should be from 1. So try the ratio test on the absolute value of the power series and see what you get. Okay, okay. Turn to somebody nearby and say what happened, because something interesting happens, I think. I don't know if it's interesting. I think it's interesting. Okay, so let me see if I can make the idea clear again, because I think I haven't made it really clear. So you have this power series, right? You have this power series, and what we've just said is that whenever you have convergence at one point, you've got absolute convergence in this whole symmetric interval, right? You're going to have absolute convergence. So what that tells you is that it's okay to look for absolute convergence, right? It's okay to look for absolute convergence in that case, right? You're not going to lose anything, because whenever you've got convergence, somewhere, you've got this full range of absolute convergence, right? So, earlier we were saying, sometimes when you take absolute convergence, you lose something. Well, in this case, you're not going to lose. It's all right to do it. So this lemma basically says, when you're dealing with power series, go ahead and take the absolute values and use ratio test and use root test. Okay, so that's what it says. So here you've got this power series, and so you take the absolute values and you do the ratio test on it. Okay, so let's do it, right? So somebody gives you this, and you say, oh, it's a power series, so I'm going to use the ratio test or the root test on summation x to the n over n, right? And what happens when you use the ratio test? Well, you get the limit of, who can tell me what happens? What do I get? When you do the ratio test, who remembers, does anyone remember the ratio test? Does anybody remember the ratio test? I'll try to look disappointed. Okay. Actually, I'm really disappointed, but it's okay. Yes. What do you do? Antigen, yes. Huh? What do I do here? I take the limit of. Jin Xiaojing, do you want to help or translate?
n plus 1 over n.
Yeah, so you take the n plus 1th term, right? N plus 1th term, so you take the n plus 1th term, you divide it by the nth term, right? And you take the limit as n goes to infinity, right? Okay. So what do you get? You get the limit as n goes to infinity of x to the n, x to the 1, right, over n plus 1 times n, right? What's that? Absolute value of x, right? Absolute value of x, right? And remember what the ratio test says. What does it say? As long as the ratio is smaller than 1, you have convergence, right? Ratio test says as long as the ratio is smaller than 1, then you have convergence. If the ratio is greater than 1, then you have divergence. Right? So what does that tell us? That this thing converges, right? So that tells us that we have absolute convergence between -1 and 1. Right? I should do it over here. Let's go to left. Okay, so we have absolute convergence of this guy from -1 to 1, right? In other words, we get the radius, radius of convergence is 1, right? Radius of convergence is 1. Okay, and at this point, you do need to check the endpoints. Right, you need to check what happens at -1 and what happens at 1. Okay, because at this point, all we have is that, we have the inside of the set, but we don't have the endpoints. But you just do what we did over here, right? You see that at -1 it diverges, at +1 it converges. Okay, so in the end, ultimately, the circle of convergence, the interval of convergence is -1, 1, with the left side open and the right side closed. Okay. Just for what would happen if we use the root test? Just for experiment. What about if we use the root test? We would take the limit of the nth root of the nth term as n goes to infinity, right? And what do you get there? Somebody just tell me, what do you get? What do you get? Come on. It's just algebra. It's just elementary school. You get absolute value of x over the nth root of n, right? As n goes to infinity, what happens to the nth root of n as n goes to infinity? It becomes 1, right? So we end up with the absolute value of x again, and again you get the same thing, right? This converges, so that the root test tells you that the series converges if this is smaller than 1, right? Same thing. You're going to get the radius of convergence is 1. And it should be, right? Because we already saw that it was 1. So we see that you get the same answer from a different method. Okay, let me ask you to do, here's one for practice. Summation, let's say, n, x to the n over 6 to the n, from n equals 0 to infinity. Okay, so try whatever test you like, root or ratio, and see what the radius of convergence is. It should take you about 1 minute. Okay, turn to somebody nearby and say what the radius of convergence is. Okay, what's the answer? 6. 6, right? Everyone gets 6? Right. If you look at this, I would say probably root test is, jumps out. Like, clearly, I want to use the root test. So I apply the root test to apply the root test to the absolute value. Right? And you get the limit of the nth root of n x to the n over 6 to the n as n goes to infinity. Right? And you end up with n root, the nth root of n times, whoops, I forgot the absolute values, absolute value of x over 6. Right? Which turns into the absolute value of x over 6. Right? And the root test says, as long as this is less than 1, then we're good. Right? Then we have convergence. So as long as rho is less than 1, in other words, x has to be in absolute value less than 6, we have convergence. Okay. And if we're bigger than 1, then we don't have convergence. Right? So we know that the radius we know that the radius of convergence of this guy, n x to the n over 6 to the n, from whatever it was, 0 to infinity, is 6, right? So we have convergence from -6 to 6, and we have divergence outside here, but we actually don't know about the endpoints. We have to check the endpoints again. Okay. So what happens at x equals 6? What happens at x equals 6? We're going to have what? Divergence, right? Why? Yeah, we're just going to summation n, right? Summation n, which very much diverges. Right? What about at -6? Again, divergent. How come? We'll get, we will get, well, it's not negative n. What you get is, at -6, you're going to get -6 to the n over 6 to the n times n. Right? So you get -1 to the n, n. summation, right? That does diverge. Why? Why does that diverge? Jump into it. Alternating series test will tell you when it converges, but it doesn't tell you when it diverges. We actually have a
Because it's error and it's over and
Can anyone explain? We have something called the nth term test, remember? The nth term test says if your term doesn't go to 0, then you diverge, right? And here you have, your term does not go to 0, right? It starts bouncing back and forth between bigger and bigger numbers, right? Like you get 10, negative 11, 12, negative 13. 14, negative 15. It starts getting bigger and bigger, right? So it doesn't, negative 1 to the n times n does not go to 0, so diverges. Okay, so what does that tell us? That tells us that these guys are out, right? And the actual domain of convergence is between negative 6 and 6, right? The endpoints, neither endpoint worked, right? So the domain of convergence is negative 6, 6, the open interval negative 6, 6. Okay, another example, negative 1 to the n. This one is a little bit different, and you'll see something happen. N squared, 3 to the n, x plus 2 to the n, summation n from 1 to infinity. Okay, so apply some test to this, whatever test you like. Typically, root and ratio are the ones they use. In a later course, you'll find out that root test, a sort of special modified root test, always works. Although sometimes it's hard to use. Okay, turn to somebody next to you, turn to somebody nearby and say what you're getting. Okay, who would like to give me the answer? Wait, nobody was talking. Maybe you're still working. Okay, one more minute. Okay, talk to somebody nearby, please. Okay, who would like to say? Wang Qingchang, how about you?
X is more than 2, bigger than -4.
Tell me what you did. So what test did you use?
Plus -1.
Are you using the root test or the
Yeah,
rate?
root test.
The root test? Okay. So let's take the limit as n goes to infinity of the nth root, right? The nth root of the absolute value of this, right? So you take the absolute value of x plus 2 to the n over n squared 3 to the n, right? Take the nth root of the absolute value, right? So maybe, actually, I think it's somehow clearer if I write x plus 2 to the n, everything to the 1 over n. Okay, so what do you get? Get the limit as n goes to infinity. The top becomes x plus 2, right? And then the bottom, what happens to the bottom? Well, we're going to get n to the 2 over n, and we have a 3, right? Okay, as n goes to infinity, what happens? Well, the x plus 2 stays still, the 3 stays still, right? Neither of those things has to do with n. So here we have this n to the 2 over n. What's that? What happens to that? That becomes 1, yeah, that becomes 1. Right, so we end up with x plus 2 over 3, right? And so the root test says this has to be smaller than 1, right? Okay, so this has to be smaller than 1 for convergence. Yeah, so x plus 2 over 3 has to be between -1 and 1, right? In other words, x plus 2 has to be between -3 and +3. Right, let me say it this way. We know that the absolute value of x plus 2 must be smaller than 3, right? Right, so what does that say? This is the distance to -2. Distance to -2, right? If you have, x minus a, that's the distance of x to a, right? So this is saying the distance to -2 has to be less than 3. So here is -2, 1, 2, 3, 1, 2, 3, right? Right. That gives us this interval -5 to 1. Okay. From -5 to 1. Okay. Wang Qingchang, I think you said like -4 or something. How come?
Wrong number.
How come? How come? What happened?
Just I write the x plus 1 and 3.
Oh, you wrote x plus 1. Oh, okay. Okay, that's fine. Very good. Yeah, if it were x plus 1, then yeah, it would be from -4 to 2. Very good. Yeah. Okay, so that is the first part. We get the this is actually called the interior of the set of convergence. Set of convergence. This is the